Okay, so if you remember, last time we we proved that T delta U, T gradient U minus U gradient T dot dA has to equal to T Laplacian U. Let me move this a little bit to the left here so we can have more room. Minus U Laplacian squared T. And this was a volume integral here. And this here is d tau. And this was a surface integral. Okay. Now, if you remember, the way we did this is we said what if V is equal to dt gradient U, right? And so and V1, and we called T1 or V2 U gradient T. And so if we plug these on the left hand side, so T gradient U minus U gradient T dA just becomes surface integral, right? Of T gradient U, we call this one V1 dot dA, and we can split this integral into V2 dot dA, right? And then, if you remember, we used the divergence theorem. And what the divergence theorem does, it allows you to change a surface integral into a volume integral. Either way, I mean, it's an identity, so you can take it either way. And so in this case, right? It depends on the use. Like, so for example, here, I would want to do it the other way around. So I need to, because I'm trying to prove the right hand side, which is a volume integral. So I need to use the divergence theorem the other way, which is V1 dA, right? V1 dA becomes the gradient, right? It's in the back cover of your book. V1 dA becomes the gradient or the divergence, right? The divergence of V1 d tau, and this here becomes volume integral. And then I can do the same exact thing on the second one. The divergence of V2 the divergence of V2 d tau. Okay. And now if I bring back the v1 and the v2, correct? So now bring them back. So so this becomes triple integral divergence. V1 was t delta u, t gradient u, and minus. Same thing here. V2 was u. Okay, and now we can use the product rule to distribute the divergence. And so if I remember the product rule, 1 second here, let me just. Okay, so this is product rule number 5, yeah, that we see. This is the divergence, and so in our case, of course, the gradient is the A, and the T is the F. So if we do this, let's start at the beginning here. Right, you get F, which is T, divergence of the gradient, plus A, which is the gradient of U, dotted with the gradient of T. Right, so T is acting like F, and the gradient of u is your vector function a. This a here is a vector function because the gradient is a vector, and the other one is a scalar function. Okay, and we forgot the d tau here, so there's a d tau. Okay, and then this whole thing is d tau, and we could do the same exact thing on the other one. Minus, except here you switch the role of the u and the t, because notice the only difference is instead of having u gradient t, you have, instead of t gradient u, you have u gradient t. So you just switch them. Basically you're applying the same rule, product rule number 5. And don't know if I have enough space here, so let me continue here. So minus v, we will get u t, there's no dots here, right, plus the t, and there's a minus sign, I'll distribute it in a second, and this whole thing is d tau. Yeah. Okay, and so we get let me use a different color. Okay, so we have t. What's the divergence of the gradient? That's just the Laplacian. Okay, so these two becomes the Laplacian plus so this is d tau. I can distribute the integral and then I have another one, du gradient u gradient t d tau minus, and here I have u, the Laplacian of t, d tau, plus or minus, because the minus sign will distribute, so gradient t gradient u d tau. And you can see that these two are the same and they cross out, and what we will have left is t Laplacian u d tau and a volume integral minus u Laplacian squared t d tau. I can combine these two under the same d tau, and we have this here. Okay, right? Okay, so this is changing a surface area into a volume, a surface integral into a volume integral using the divergence theorem. Now, and you know, with the same exact logic, if you remember, except it was one of them, we did prove last time. It follows from the same very logic that the integral, the surface integral, the surface integral of t gradient u dA, which sort of we already done on one of them, turned out to be just using the divergence theorem, the volume integral of t Laplacian squared plus gradient t dotted with gradient u. Okay, this was sort of the first part of the proof. On our way to prove this final result, we kind of went through this. So this was d tau. Okay, so let's actually, so this is the critical part. Let's go ahead and use this to prove the second uniqueness theorem. Right? That's the idea. So so the second uniqueness theorem says that in a volume V surrounded by conductors and containing if you know the specified charge density rho, the electric field has to be uniquely determined if you know the total charge on each conductor. Okay, and so this is the second uniqueness theorem, which means there couldn't be more than one electric field, and it exists. So if you were to arrive at that electric field by any means, by any method, and it works, it has to be the right one. It has to be the right field. Okay, and okay, so let's use these results to say that. Well, so why don't we assume that there's another electric field, a third electric field, yeah? So in other words, what we said originally is so suppose that we have some conductor here with Q1 and rho is specified, yeah, surface charge density, and there's another Q2. So this one here is Q1, Q2, and this is our V, Q3, etc., Q4. Okay. And now suppose there are two fields existing here, right? So both have to obey Gauss's law. So that means if there is, then the divergence of E1 has to equal to 1 over epsilon volume charge density, and so does E2, which is 1 over epsilon surface charge density, right? And so this is the Gauss's law in the differential form, and you also have to obey Gauss's law in the integral form. And so if you were to take any one of these conductors that you have inside this volume, and if you apply Gauss's law on that surface, whatever surface you have, yeah, let's take the nth conductor, yeah, and you take a Gaussian surface on that, then your E1 dA, right, E1 dot dA has to equal to the Q on that conductor. Let's call it Qn if you know the nth conductor is enclosing charge Qn over epsilon, right? And also E2 dot dA on that same surface on the nth conductor has to equal Q enclosed, so Q that conductor encloses over epsilon. Okay, and so let's say we have an outer boundary, and you know this is defined by our outer boundary here. Okay, so you know this could be inside your conductor, or this could be at infinity. Doesn't really matter. So so let's call this boundary. What are we gonna call it? S. Let's just call it S. Also, Gauss's law has to apply. So on S, you're supposed to have E1 dot dA on the outer boundary on S has to equal the Q total that boundary encloses over epsilon, and likewise E2 dot dA on S has to equal Q enclosed over epsilon, right? Or Q total if you're enclosing the whole thing. Okay, and so why don't we look at the difference? Let's call E3, or let's say let E3 equal E2 or E1 minus E2, right? And so you know the divergence of E3 has to equal to the divergence of E1 minus the divergence of E2, and since both of them are zero, since their difference is zero, because this is 1 over epsilon rho minus 1 over epsilon rho, so this is equal 0, right? Okay, and so in any region between the conductors, you'd have to have E3 dot dA equaling 0. Okay. Now so that's E3 dot dA equals 0, the integral of E3 dot dA according to Gauss's law. The difference between the two electric fields, if you were to integrate that over the area, that would get you 0. Now we know that those conductors are equipotentials, and we know that any potential that they have has to be constant, right, over each conducting surface. Doesn't have to be 0, but you know, they don't have to be equal, but they're constant. Okay, so if that's the case, then okay, so at this point what we do, Ben, is if we take the divergence of V3E3, okay, and we'll use the same rule number 5 that we used on the distributing the divergence. So this will be V3, so that's the potential divergence of E3 plus E3 V3, and well, we know that this guy is 0, and so what we have left, and what's this guy here? This guy is E3 or minus E3, right? Because the gradient of the potential is the electric field, so we get minus E3 squared. Yeah. Okay, and now why don't we integrate this? So if we integrate this, d tau, okay, we know what the answer is going to be based on the above analysis. This is just E3. Yeah, well, first turn it into a surface integral, right? The divergence, using the divergence theorem, so this is just V3 E3 dot dA. So going from a volume integral into a surface integral. And we just proved that this is nothing but E3, negative E3 squared d tau, right? Okay, well, look, we have proved I mean, the only way this could be this has to turn out to be 0, right? Because we said that E3dA is 0. So so this guy is supposed to go to 0. So we have E3 squared d tau equals 0. Now the only way that this can happen, this is positive and this is positive, and the only way you can get 0 is if E3 equals 0. And if E3 equals 0, that means E1 minus E2 has to equal 0, which makes E1 equals E2, the electric fields are unique, and therefore no two different electric fields exist, and it has to be only one electric field. And so we'd have proved the uniqueness theorem. So E1 has to equal E2, and there's only one electric field. Now, so this is what Griffith got. This is kind of the logic that Griffith used to prove the uniqueness theorem, right? Now, if we go back to our identity, we can tweak this in a slightly different way here on what we proved, and we can say, okay, well, up to where V3 is, so we can start here, yeah? Why don't we set U equals T, and we call that our V3, because those are scalar fields, and we plug it into Green's identity, right, which we proved up there. So if we plug it into Green's identity, which is this here, on the right hand side of this, yeah, so we replace every T and every U with V. Okay, so now going a slightly different route than what Griffith used to prove the uniqueness theorem, we're going to be using Green's identity, and if we do that, what we will get is V3 Laplacian of V3, yeah, plus, if you remember, so this was U Laplacian T, so now since they're all equal, it's V3 Laplacian V3, and the second part was I think the second part was gradient T gradient U dot gradient U, which in our case becomes gradient V3 dot gradient V3 d tau. Okay, and this is a volume integral, so this is technically a triple integral. Yeah. Okay, now what does this equal to as a surface integral? This, if you remember, the left hand side of this was T gradient U dot dA. That's how we got to the right hand side in the first place. So again, using the divergence theorem and turning this into a surface integral, so this is S, right? Now T is V3 and U is V3 dot dA. Okay, but remember, we called E3 to be E1 minus E2, and therefore what's E3? E3 is the gradient of V3 to equal the gradient of E1 minus the gradient of E2. Oops, wait, sorry. Gradient of V1 minus the gradient of V2, because gradient of V1 is E1 and gradient of V2 is E2, right? But I could take the divergence of this, right, one more time. So I could say the divergence of gradient V3 is equal the divergence of gradient V1. If the gradients are equal, the divergence of these gradients have to be equal. Yeah? Minus the divergence of V2. And so this becomes the Laplacian of V3 equal the Laplacian of V1 minus the Laplacian of V2. Okay, now what's the Laplacian of V1? The Laplacian of V1 is, if you remember, minus rho over epsilon, right? Because that's I mean that's just the divergence of E1 basically, right? Because the we've said that here. Where did it go? Here, the divergence of E1 is 1 over epsilon rho, and if you remember, E1 I replaced it with the gradient of V1, and that's how this became the Laplacian. But if you break it back into its E components, it's just the divergence of E1, and this is minus rho over epsilon minus, same thing for the second guy, right? Same surface charge, so minus rho over epsilon, and this is just what? 0, right? And so that means the Laplacian of V3 is 0, right? And what's the gradient of V3? That's just negative E3. Correct? Okay, so then in that case, going back to the integrals now. So the integral, volume integral of, so the right hand side became E3 times V3. So we've got V3 so this is E3 squared d tau, right, equals minus the surface integral of V2 E3. V2 E3 dot dA. You agree? So the left hand side is where I proved that because this guy here became just so you know, this guy here is 0, right? Because I proved that the Laplacian of V3 is 0, and delta V3 is just E3, and this is E3, so this became E3 squared d tau, yeah, and the right hand side is the surface integral is V3 the gradient of V3 is what did we say? The gradient of V3, we were able to prove that wait, I'm missing a step. Oh, it's here. The gradient of V3 is minus E3. So I replaced this guy here with minus E3 times V3. Times V3. Oops, this is supposed to be V3. Dot dA. So far, so good? Okay, and so this is V3 E3 dot dA, and okay, let's see how we're gonna arrive at the final step now, or a few final steps if there are any. I mean, from here on, it should follow like the same part because we, if you remember, we arrived at the same place last time when we used the first method. And so yeah. So minus. So now so this is V3, and what's E3? E3 is V3 E3. So this was E3.dA. So yeah, exactly. So this became V3, and V3 is what? The gradient of E3. Or E3, oh sorry, E3, so yeah, so this is delta 3, and E3 is just the gradient V3, and E3 is the gradient of V3, right? Dot dA.
She didn't put that phone number, 818-497.
You see? Let me just get a cup of water really quick though. Okay, so we said that this guy here is constant, so we can bring it outside the integral, yeah, if it's constant. And then let me just leave this as E3. So this is E3.dA, right? But what's E3.dA? Well, we said the first time that E3.dA is 0, right? Because you're inside a conductor, and or in the region between the conductors. So over each boundary surface, this has to vanish. Correct? And so if this guy is 0, then bring this down. We go back to the first one. So E3 squared dot d tau, V3 times 0 is 0 over V. And since this is a positive number and this is a positive number, the only way that those two can integrate to 0 is if E3 equals 0. And again, if E3 equals 0, that just means E1 minus E2 equals 0, which makes E1 equals E2. And the second uniqueness theorem is verified. There can't be two unique fields, two fields or more. There has to be a unique field that specifies what's going on there. You see? So so the second part, starting here, we did arrive at this conclusion using Green's identity, which is what we proved initially.